Hello and welcome to Honors Chemistry. Today we're going to be doing our first flipped lesson where I'll be talking through a PowerPoint with some basic knowledge, and then the following day in class we'll be applying that knowledge in small groups. You can see here that the honors expectation is that you are looking through your textbook periodically, specifically right now at chapter 1 and 2 on your own time, but today we will be really focusing on chapter 3 because that is going to give us a glimpse into the math that's involved in chemistry. So before we do that, this is a glimpse of what's in chapter 1. It talks about how chemistry has evolved from the early eras until now. Initially, there were people that we called alchemists that were the ones responsible for developing some of the first tools of chemistry. Some of you guys have maybe even read The Alchemist, the book. And so the initial tools and techniques, even things such as distillation, filtration, some tools that we actually will use in class, they were developed a long time ago. And so they used to believe that chemistry and science was the working of kind of a mystery, magical sense. And so we've since then said, no, everything we have here has a logical explanation. There's no mystery or magic behind it. One important figure in science was Antoine Lavoisier, and he actually did a lot with the law of conservation of mass, which some of you might know is that matter or mass is neither created nor destroyed. It simply changes form. So you can see I'm talking a lot over this video, and so if you have this PowerPoint or the PDF that's been printed for you, then you should be jotting down some of the terminology that I'm speaking about right now. We also credit Mr. Lavoisier for identifying hydrogen, which is H2, it's a diatomic gas, and oxygen. So he coined the terms for those. He also found that these things occurred in integers. So there's no like half of an atom of hydrogen or half of an atom of oxygen. They're in whole units. And you can read more about him on his Wikipedia page. He also dealt with a lot of combustion experiments, and he analyzed the products of combustion. Some of you guys might know that combustion is just taking something that's a sugar or a hydrocarbon, so a hydrocarbon, which has hydrogen and carbon in it, as you might imagine, and you add it to oxygen, or you put it in the presence of oxygen, and it naturally combusts, which would then create carbon dioxide and water. So that's the generic equation for a combustion equation. So he obviously dealt a lot with oxygen, so he dabbled in combustion as well. All right, so these are some quantities that you actually might be familiar with, but we're going to walk through the SI system of measurement because that's something that respects the consistency of science around the world. And so in order to be able to publish information to the world, the scientists of the world, we need to have a common language. And so the common language in the math side of things is going to be the International System of Measurement, or the SI system. One thing that you want to note is that a measurement will not only include a quantity, which is a number, it will also have a unit. And so you can see the units are down here denoted by a specific symbol. Things that you will use most often are meter, kilogram, which is a unit that describes the mass of an object. We eventually will get to amps or amperes, but that's going to be a little while. Kelvin, which is a unit that describes the temperature of an object or some matter. Mole will be a common unit for us in a couple of chapters. And lastly, volume. So liters or milliliters can be used. The liter and milliliter denote a unit of volume. So all of these here, you can see they only have a single unit. Now it might be milliliter, but it's still just the unit liter with a prefix milli in the front. Occasionally we have to derive our own units, and an example that you might be familiar with is that of density. So density, you can see it's not a measurement up here, but it includes mass and volume from the measurements above. However, it has a little bit of actually division in this case, but it's got some sort of calculation around it. So density is equal to mass over volume. And so another one you're familiar with is going to be area. For example, area of a square, side times side, or side squared. And if we're talking about length here, length is going to be denoted in the unit meter. So meter squared would be our unit there. So the term derived, it just means that we have to do a calculation in order to achieve it. So you probably have noticed that I'm not really going to mention Fahrenheit at this point. So Fahrenheit is going to be more of a US term or a unit that we use a lot to describe the temperature of a room or even looking at our weather. Celsius, some of you guys might be a little comfortable with, but I want you to get more comfortable with the term Kelvin because that's the unit of temperature in chemistry. And it's derived from Celsius, and so you can see that the conversion is very easy. You just add 273 to Celsius and you get your Kelvin temperature. So take a second and calculate the temperatures, room temperature and body temperature in Kelvin. So you should be doing for room temperature 25 degrees Celsius plus 273 to get 298 Kelvin, and then you guys can do body temperature. Yes, you should know that room temperature is 25 degrees C. That might be a new one for you, but I do think that you should be familiar with water's boiling point being, you're probably thinking 212 Fahrenheit, but that is 100 degrees Celsius. And you're probably familiar with water's freezing point being 32 degrees Fahrenheit, which is 0 degrees Celsius. So be familiar with the new one of room temperature, body temperature. We won't really reference all that often. Okay, so the metric system is what we use for the prefixes that go in front of the SI units. And so you saw one already, kilogram. So the kilo was denoting the size of the unit that was denoting the mass of an object. So gram is talking about mass and kilo is just the prefix in front of that unit. So some of you guys maybe took biology and you heard King Henry died by drinking chocolate milk. So King, K, Henry, H, died, Deca, by drinking chocolate milk. And so that's the easy, cheesy way to remember the order of the prefixes. The one that's rough is base, the base unit. That doesn't really say a prefix. That's saying that doesn't have a prefix. That's gram by itself, meter by itself, and liter by itself. Yes, we have other base units like you can see in the SI system, but that's generally what we're going to talk about at this point in time. So everything with a capital letter, those are larger units. Those are bigger than base. Everything with small lowercase letters D, C, and M, those are smaller units, and that's smaller than the base scale. Now, that's what you used to maybe be familiar with. We're going to tack on a couple more prefixes that denote smaller and smaller and smaller units that we will be using throughout the course. And so here you go. Let me remove this. You can see that the extras are on the tail end. So I'll start here. King Henry died by drinking chocolate. Oops. Henry, goodness gracious. King Henry died by drinking chocolate milk. And then dot, dot. These dots are placeholders. They are zeros, but we don't need to know those prefix terms. Okay, so after milk, you get dot, dot. This one's micro. Dot, dot, nano. Dot, dot, pico. Like a picometer, a nanometer, a micrometer, or micrometer is what some people say. Those are going to be smaller units than milli, which is the last one in that little cheesy drinking chocolate milk thing. Even larger than kilo by 1,000, because you can see that there are 1, 2, 3 spaces in between kilo and mega. So a mega meter, for example, is 1,000 times greater than a kilometer because it's 3 zeros away. And a micrometer is 1,000 times smaller than a millimeter because it's 1, 2, 3 spaces away. Yes, you're probably looking at this micro symbol. It's a U with a tail in the front. So it kind of has a funny look to it. All right, so the reason we need to know that all of these zeros or placeholders exist across this number line, across this metric system, is because it helps us with conversions. And we will be converting a lot in some of our later units. However, right now I want you to get comfortable with using the metric system. So for example, this first question says I have 53 grams and I want to convert it to the unit of kilogram. Well, you're probably thinking in your head, okay, a kilo is bigger than the base unit that I have right here in the middle. I'm going to change colors for us here. So kilo is bigger than base by the nature of 1, 2, 3. So it's 1,000 times bigger. Well, that makes sense. But what we can do is we can actually say there are, so the difference is there's 3 spaces, 1, 0, 0, 0. And these numbers correlate with each of these letters. There's 1,000 grams, which is what base represents, in a single kilogram. So what you do is you simply write that as a ratio. And I'm going to put times the ratio. But I need to do this so that in the end I get kilograms on top. And that's the unit I'm looking for. So I'm going to put 1 humongous kilogram has lots and lots and lots, 1,000 to be specific, grams in it. So what happens is the gram that's on top over here and the gram that's on the bottom here, they cancel each other out because they're anti to each other. The only unit left is kilogram, so when I plug this in my calculator, or you can maybe do this in your head, 53 divided by 1,000 is 0.053 kilograms. Then you should question yourself, does this make sense? Yeah, it totally makes sense. There's 1,000 meters, or excuse me, grams in a kilogram. I got 53. That's not even close to a full kilogram. And so that's why you can see it's a decimal number. Next, we have one using liters and deciliters. So let's start again. 9.84 liters multiplied by, let's look for these 2 units and look at the significance between the two. Back to our number line, I'm changing color to blue here. Liter is base. Deci is right next to base. So it's a difference of 10. But the base is 10 times greater than the deci. The liter is 10 times greater than the deciliter. All right, so that means down here, we're going to put liter on the bottom and deciliter on top because I need to cancel these 2 liters. Remember, the liter is bigger. You have 1 liter and it has 10 little deciliters in it. It helps rationalize it. So the 2 liters cancel. The number does stay here. It's just divided by 1. So in the end, we're really just doing 9.84 times 10. That's 98.4 deciliters. And there should be more deciliters because they are smaller in quantity. Scientific notation is something you're probably familiar with, and it's just a trick for us to not have to write as much. Generally, it's going to be dealing with large numbers and small numbers and writing them in a convenient way. So this very, very large number is ridiculous to write out over and over again. So what we need to do is we need to find a coefficient to be the beginning number, and then we're going to multiply it by 10 to some some exponent in order to give us the correct quantity. So take a second, pause the video if you need to, and go ahead and write this in scientific notation. So if you're counting all the zeros, you're going to see there are tons of them. So the number you most likely chose, which has to be a number between 1 and 10, will be 6.02. And all of these zeros afterwards may or may not be needed in order to write the size of the number. So to get away with not writing them, we're going to put times 10 to the whatever this zero first is to whatever this last zero is. That gives us 23 spaces in between. So 6.02 times 10 to the 23rd. Let's do a couple more. So pause the video and do the highlighted ones 1, 3, and 4, and write these in scientific notation. All right, so it looks like we're back here. I'm going to go ahead and write this in scientific notation for you to check your work. So I see that the first number I can get to that's going to be between 1 and 10 is 3.88, but I'm going to continue 09083 because all of these numbers are important to the actual number here, the value here. However, 3.880983 is definitely not this number. So we need to go ahead and multiply it by 10 to the exponent. That's going to get us back to where this decimal lives actually. And you can see that's 1, 2, 3 spaces away from where I artificially put it. So since that's in the reverse direction, we're going 10 to the negative 3. 805,000 is 80 or 8.05, and then times 10 to the 1, 2, 3, 4, 5. And since that's a larger number, it's a positive exponent. Now this negative may have thrown some people off, but really it's just a negative, and then you put 6.895, which is the integer that we have to denote, times 10 to the 1, 2, 3, 4, 5, 6. And since it's a smaller number, 10 to the negative 6 will do. Now these are all just numbers. These are not actually measurements because they don't have a unit. Alright, so I will do one of these for you. If you want to pause the video and do it yourself, that would be great. Alright, looks like we're back. So if you're going to be writing this in scientific or in long form from scientific notation, the only thing you need to do is take the decimal point back the number of times that this exponent says. Because it's negative, that's what we're going back. 1, 2, 3. And so that would be 0, 0, 6, 8, 9, 2. So that's 0.006892. Alright, so we're probably okay with scientific notation. If you need to review that, please come to tutoring. Accuracy and precision. These are two terms that most people use pretty interchangeably. However, they're not the same thing. So if you think about Michael Jordan and you think about what's his accurate choice when he's playing basketball, it's probably to get the ball in the hoop. So he wants to see how close he is to the true value, which is the hoop in this case. So he wants to get it in the hoop. That's the accurate place, the accurate value, for example. So he can be at the free throw line and keep shooting and shooting and shooting and shooting and hitting the upper right hand side of the backboard. Maybe he's over here and he just keeps hitting the board right here. Well, he's very, very, very precise, but he's not accurate because he's not in the hoop. So precision is a series of measurements, or a series of shots in his case, and it's how close the series is together. So if you keep airballing the whole time, it's really precise, but it's not accurate. So there's a way you can think about it too. You can be precise and be accurate. But you can also be very precise, but not accurate too. Think about that. Similar, a lot of times in our measurements, we also can have error. And error is the difference between what you want, which is usually the accurate value, and what you're getting, which is where you continually measure or where you're shooting the basketball. So the difference between the accepted value and the experimental value, which is the value that you get in the lab, for example, the difference between that is going to give you the error. However, in order to get percent error, you need to take those values in your subtracted form, divide it by your accepted value, and times by 100, because all percents always are multiplied by 100. So this formula is very important to remember. Very important. So please write that down. Accepted minus experimental over accepted times 100 is how I remember it when I write it in shorthand. And you'll notice that these absolute value brackets here can allow me to write A minus E or E minus A. Either way will work because you're doing the absolute value. So a quick example will be related to our room temperature measurement that we are measuring, and we measure it to be 28 degrees Celsius. Well, if we measure it, we are experimenting, so this is our experimental value. And if you think back to the very first, one of the first slides, you'll see the temperature was 25 degrees Celsius for the accepted value of room temperature. So go ahead and pause the video, plug your values into your percent error calculation, and find your percent error. All right, hopefully you've had a chance to do that. The percent error would be accepted, in my case 25 degrees Celsius, minus experimental 28 degrees Celsius, divided by the accepted value of 28 degrees Celsius times 100. So that's going to be 3, because absolute value over 25 times 100. You guys can fulfill that calculation. This is a good slide to just read over. It's a good explanation of the real difference between precision and accuracy. And you can see in green here the two phrases that I think work the best. So precision is an indication of the reproducibility of measurements. So that's the series of measurements you have over and over and over again. Separately, accuracy is going to tell you the nearness of the measured value to the true value. So how close you are to the true value. And you can read the rest of that. Okay, so moving on, significant figures is an important part of chemistry. You may have been exposed to these once or twice in your life, but it's probably fairly new. So you're going to be seeing a couple of rules that relate to using significant figures in chemistry. How do we measure things and not lie about our measurements? How do we do calculations and not lie about our calculations? I know you're not trying to actually lie with your calculations and measurements, but some people accidentally go, oh, well, my ruler says this cube is 1.255555555 centimeters long. None of our rulers are that accurate. Like, that's really accurate. There's a lot of digits in that number. So we try to say the number of digits we need to not mislead our audience when we're telling them what our numbers are. So we want the most accurate values when we do measurements, but we always allow for 1 digit of wiggle room. So if you're measuring something and the ruler only goes from 0 centimeters to 1 centimeter, and you have a cube and it measures, from here all the way over to here, well, you're going to say it's 1 point, and then the wiggle room is, you don't know, maybe it's 1.1, maybe it's 1.2. I'm going to say 1.2 centimeters. But that's it. That right there, that 2 is the estimated digit. That's an estimation. Now, I said 1.2, whereas you could have said 1.3 or 1.1. But notice I'm not going further than that because I can't estimate 15 more digits. I don't have that kind of accuracy. So whenever we're talking about significant figures, or sig figs, how is a short way of writing that, sig figs, we're going to include all the digits that are known because the ruler said so, plus the estimated digit that we have the freedom to estimate. So these significant figures, the number of numbers or digits that you include, really depends on the apparatus scale. So the apparatus is the tool that we are using. So you can see these two rulers here. This one over here, this is a great one. Look at all these little graduations and dashes along there to give you some estimation power. This one's a crappy one. It's not very good. There's really nothing we're able to work with here because it just doesn't have any graduations on it. So that's what we're saying. This little brown block here, you might have to estimate, guys, I don't know, 1.4? I don't know. 1.4 centimeters is what I'm going to claim. But I can estimate to the 4 and that's it. But this great ruler, ooh, it says it's 1.3 exactly is what it looks like. Because that's what this 3 mark is. But then I have the power to estimate one more digit. 1.30. And so that gives me the estimated digit of 0, whereas my estimated digit over here is 4. This one is more accurate because I am closer to the actual value. This has already been printed in your lecture notes. This is a series of rules that help you to decide the number of sig figs in a measurement. And so I'm going to go ahead and walk through some examples with this, and you will also be able to practice on your own. So the Pacific Atlantic method just is a little silly rule that gives you some information about if you're starting from a decimal that is present, you start from the Pacific side, which is the left side of the number. And if the decimal is absent, meaning you have a number like, I don't know, 1,000, no decimal here. Decimal is absent, you start from the Atlantic, which is the right side of the number. And you can see that whenever you start counting sig figs, you start counting at the first non-zero digit from whichever way you are actually counting from. So don't count the zeros unless it says to, meaning it's in the middle of the number someplace. So let's go ahead and look at these. These examples are on your worksheet as well. So remember, this is the Pacific and this is the Atlantic. So the first three I'll do with you. Notice, point out to yourself, is the decimal present or absent? So this decimal is present. So I'm going to start counting from the right-hand side, which is the Atlantic. So as I count, I start counting sig figs, the number of digits, at the first non-zero digit. And that happens to be the 7. So I'm going to start counting at the 7 and then see 1, 2, 3. So I see 1, 2, 3 digits. Because as soon as I start counting, you don't stop. And so there are 3 sig figs in this measurement. That's pretty good. All right, so again, step 1, is the decimal present or absent? The decimal is present. Oh, gracious, guys. Let me redo this first one. I just said present, and I did absent. Okay. Rewind. All right, so decimal is present, as you can see right here. So we're going to start from the Pacific. And again, this number is interesting, this measurement, because it's going to have 3 sig figs, 1, 2, 3, from both directions that you count. It's mainly because it doesn't have any leading zeros or ending zeros. All right, let's go ahead and go down to the next one. All right, so the first question, present or absent, it's definitely present. Start from the Pacific, start counting the first non-zero digit. 1, 2, 3, 4. So you are counting those zeros because once you start at the 9 and the 7, you don't stop counting because everything after that gives it more and more accuracy. There are 4 sig figs in this question, in this measurement. Next, present or absent? It's definitely absent. All right, absent again is the Atlantic. So we're going to start from the right-hand side. So as you're moving towards the number, you're like, oh, got to count the 6, which means you have to count everything after that. And so 6, 0, 0, 2, and 3, all of those are significant figures or digits. So there are 5 sig figs in that number. 1, 2, 3, 4, 5. Go ahead and pause the video and take a shot at some of these below. All right, hopefully you have paused the video and you've tried. I'm going to selectively do 2 or 3 of these. I'm going to start with E. Notice that the decimal is absent. So you're going to start from the Atlantic. So when you start from the Atlantic, you notice you start counting the first non-zero digit. That's a 0. That's a 0. The first non-zero digit is the 2. 2 and 1 are the only sig figs. There are 2 sig figs in this measurement. Let's go ahead and do H. H, the decimal is present. It's right here. You start from the Pacific. So when you start from the Pacific, you start counting the first non-zero digit. Skip, 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 2. So just the 2 is a significant digit. And then the last one I'll do is I, and you'll see that we have a weird situation. The decimal's just here at the very end. There's no 0 afterwards, but the decimal's still present. You still start from the Pacific, and you still count everything after the first non-zero digit. So start counting the 4 and everything past that. 4 sig figs. We will be working with sig figs a lot, so I hope that you will ask questions as you need to in order to be successful. This last section is for you to try some more. I suggest that you try them, and then we will review the ones that you had issues with in class the next day. Thank you.